Hey everyone, just wanted to first say thanks for coming out. I know there are several interesting tutorials going on right now, so thanks for choosing this one. So today I'm going to be talking about multimodal AI and specifically some of the groundwork and how it operates under the hood. Then we're going to dive into some practical examples and hopefully in the process learn some of the fundamentals about how to use multimodal RAG and multimodal LLMs and even other deep learning models that combine multiple modalities. So I don't know why it's cycling through like that. Let me just try that again. So background. So first, this is kind of the overview of the tutorial. Like I said, we're going to go through some background, explore this AI project I'm specifically working on, and then kind of go into detail on that. And I'm going to highlight specific areas where where multimodal AI works well and where it doesn't, and kind of if you're deploying them in your kind of RAG systems and production level systems, what you should be aware of. Even though these are targeted towards this project, I think they're very generalizable ideas that will help you out a lot in all the AI work you're doing with multiple modalities. Then finally, we're just going to look at kind of the frontier, what's cutting edge, what's coming, and because a lot of the work, as you probably know, has been focused on text and images, but really there's a whole other side to multi-modality beyond just text and images. So first, a bit about me. I really don't know why the slides are cycling through like that every time I change. So I'm currently work as the lead AI engineer at William Blair. We're a finance company, mainly focused in investment management. So as you can imagine, we have a lot of documents that are very highly structured tables. So a lot of the things we've discovered there, and I've discovered over the course of working there, is that just using a single modality like text only does not really work because it loses the whole structure of the table when you OCR it, and then it gets things like fund names confused and a bunch of other things just using pure text. Besides that, just a fair amount of work fine-tuning for finance and things like that, which isn't really as relevant, but yeah, I do want to stress that a lot of these ideas are things I've seen directly in my day-to-day work. Beyond that, I'm also an AI researcher at this nonprofit called PolyAgent. Originally, this was known as Corona Y. It was formed during the pandemic, and it was specifically formed to kind of use AI, or well, at that point, it was known as machine learning before all the hype train came in. To use machine learning to work in conjunction with epidemiologists to kind of provide insights on the pandemic, find new research treatments, etc., and things like that. Over time, it kind of morphed into a general AI for good company, nonprofit. Specifically, there we're working on now things like democratizing access to AI, particularly on low resource languages, because as I'll talk about in a bit, really it doesn't work. A lot of the models do not work well on some of these rare languages, so how can we fine tune these models to then work in languages that there isn't as much training data on. There's also a partnership that I'm part of with Conservacorps, and Conservacorps is a separate organization specifically focused on using technology in general for disaster relief, and with natural disasters, a lot of what you see is you have different modalities of data coming in, text from on the ground, people tweeting stuff, saying stuff. You also have images and photos, satellite imagery. So really having models that can synthesize all that information is very important. Then just finally highlighting, I've now worked on free separate RAG applications. And so a lot of these ideas and insights I'm going to show today are kind of built on that experience. So moving on, before even jumping in, I assume most people are fairly familiar with the ideas of multimodality, but I did want to kind of highlight just a couple things off the start. So really multimodal, people are usually talking about text and image, but really it could be text and audio, image and time series. There are lots of different types of data, and there is kind of an overarching question of like what even is a modality. Basically data, you could choose to frame a problem as multimodal. I've seen some papers that even takes things like metadata of a document and treat it as a separate modality that needs to be fused. So really there isn't like a fine or clear-cut definition, but the standard things are usually when you have very different types of encodings of data, then you treat them as a separate modality. We'll talk about that in a bit more in a minute. And so kind of why you want to use multimodal learning is a lot of real-world problems require reasoning over multiple types of data, and often with a single modality, you lose the global context. Kind of funny example of this was last winter I actually purchased this product called Carve, which is this sensor for your ski boot that's supposed to use this sensor data to give you feedback on how well you're skiing. And it gave me a bad score and I was very frustrated, but I was skiing on a crowded slope and a bunch of people were swerving in front of me. And of course, the pure sensor data had no way of knowing that. And so maybe if it had an image or vision component like, you know, a GoPro that fed into the model, then it could reason more on just the pure sensor data. So that's kind of one example, but there's a lot more that's important for than just my bruised ego. It's also very important, say like in healthcare, if you have like CT scans of a patient, they take like both the CT scan and the doctor's freeform notes. The whole patient clinical history should be fed into the model so it can better reason across those different modalities. And finally, we have this idea of it roughly paralleling biological perception. I generally don't like this whole idea of AGI and AI thinking like humans. I think it's premature, but there is kind of a rough analogous kind of way that these models work, just as we have different senses. These models often operate with specialized encoders, so there is some biological parallel. And then finally, I just kind of highlighted that fundamental point that's fundamentally about translating different structured encodings into a unified representation space, and we'll talk about exactly how that's done in a minute. So with that said, one of the really first foundational papers on kind of multimodal AI was CLIP, or in the long form, contrastive language image pre-training, which is why everyone just says CLIP. And with that basically it had an image encoder, a text encoder, and then the different modalities ran for each. It computed this similarity matrix, and then over time what happened is it learned for the loss function to have a high cosine similarity between the text and image pairs. So like if you had in this case, in the example image, you have this, you know, Pepper, the Aussie pup, and then you have an image of this dog. It learns to have a high cosine similarity between the text embedding and the image embedding. And then that can be used for zero-shot prediction. So that's kind of the fundamentals of it. We don't have to go into too much detail, but I do want everyone to see roughly how it works. You basically, in the end, you get out these two embeddings that are the same dimension, one from the image encoder and one from the text encoder. And so basically text and images are projected first to have the same dimensionality. Then after that, there is a similarity matrix that's computed, and then and then finally it computes that loss function. The important things are this is obviously fairly complicated, and we don't have to have the time to go into every sort of detail of it, but one of the fundamental things I want people to see from this is that when we compute the loss, it's actually a symmetric loss, so it takes in both to account the image-to-image symmetry from that matrix as well as the text-to-image symmetry. So if you are using CLIP, you could actually use it for an image similarity search as well as a text-to-text similarity search because it's symmetric between the two. Some models we'll see later, like Nomics, it is not symmetrical. So that's just something I wanted to point out. Then moving on to fusion mechanisms. So like most modern VLMs now use some sort of fusion mechanism to fuse the different modalities. These really vary, but one of the most common is cross-attention. I don't know why that just went out.
It was happening to someone earlier.
Okay, yeah. So cross-attention is one of the most common. Concatenation is another. Pre-LLMs, there were even other methods to fuse modalities. LSTM, sometimes you could treat each modality as basically a time step to the LSTM. I don't know why that switched to auto, but that's kind of the idea with the different types of fusion mechanisms. So, so to get more concrete, for instance, Llama 3.2, I assume most people are familiar with Llama. It's basically this large VLM, vision language model. And so it actually uses cross-attention, like I was saying, so you'd have here an image encoder, and then it interleaves the cross-attention layer into the Llama layers. And then basically what happens with the cross-attention is you're using the, for the query vector, you're using the text hidden states, and for the key and value vectors, you're using the vision features. And so if anyone studied self-attention, I don't know if many people have, but it's basically self-attention, but then using one modality as the key and value vectors and one modality as the query vectors. So that's kind of the overall view of how it operates in this case. It's very common with other modalities too, that you have one modality be the query vector and another modality be the key and value vectors. Another model, Gemma-free. Actually, I think the last tutorial you talked about using Gemma-free, so if you were here, this is a good segue. But this uses actually just concatenation, so with image and text, it directly concatenates the two tensors into one combined tensor, and then the layers, the subsequent layers then learn how to use that fused tensor. So there's no fancy like cross-attention, it's very simple, literally just concatenate the image vector and the text vector. So then moving on to the nomics. Nomics is basically this image, is similar to CLIP in that it's used for generating embeddings that can then be used in retrieval. And so with CLIP, basically, you're going to have both, well actually I'll take a step back there. So CLIP, the fundamental difference of nomics from CLIP is basically it takes an image and then it runs it through a VLM and then generates a kind of embedding based off of that. And then the idea is then to align that with the query about what like the query with that image would be in embedding space. So it's specifically meant for search and retrieval and RAG applications, specifically made for that, not just the general embedding thing. So for instance, the image of a, say like ArcSiv paper on a vision language LLM would align with the query what are VITs or something. So then if someone then typed that in, that would have a high cosine similarity with the image embedding. So that's the fundamental difference between nomics and CLIP. It's specifically for document retrieval, and the idea is to use the vision embedding to align with the text, with the relevant textual query. Nomics has several other embedding models too. I just wanted to bring that up. Some text to text, but the idea of all their embedding models is to have the kind of saved embedding from whether it's a image embedding or a text embedding align with what the possible query vectors are. And that's how it was trained, that's how the training data was prepared in contrast to CLIP. So that will become relevant in a second later. Now I'm going to go into a brief digression as we jump into some of the practical examples. But the Cairo Geniza is like this huge trove of over 400,000 documents that was found in the basement of this synagogue in Futstat, Egypt, kind of quote-unquote discovered by the British in the 1890s, and it was then taken back to many different institutions. So now it's like spread out over 60 different institutions. It's very useful because there's been tons of different types of documents on all aspects of daily life, and it's not even just Jewish documents, there have been Christian texts found there too, but it wasn't really, it's important to know it really wasn't sorted in any way. A Geniza is almost kind of like somewhat of a trash room of documents that like that like can't be thrown out, so they have to be specially buried in Jewish religious life. So, but in the process, a bunch of documents got mixed in there, and it's a wide range of documents from the 6th to the 18th centuries. There have been multiple books and scholarship on it. They've even retraced trade routes over the Middle East and India based on it, and it's all based on this kind of set of documents. And so like here's an example one. This is a Jewish religious text. This was found in the Cairo Geniza. You can see its class mark or shelf mark. It's from the book of Deuteronomy actually. Here's another one which is a much smaller fragment that was part of it. It's currently located in Cincinnati. There isn't really much other detail on it. Here's a ketubah, or what's called a Jewish marriage contract from this collection of documents. So you can kind of see a wide variety of documents. This was another type of document currently housed in Strasbourg that was also from the Geniza, and it's basically this fragment in Greek. Again, we don't have much other info on it. And so fundamentally, there have been, like, since all the documents were dispersed between collections, they've found fragments. Sometimes one will be in Paris, another will be in Cambridge. In order to piece back together the documents and do scholarship on them, that you need to join the fragments together. So now you're probably wondering why I'm bringing this up at a PyData conference on multimodal learning. But actually the Cairo Geniza is very interesting from an AI perspective as well. For the first thing is it's probably one of the most multilingual corpuses you'll ever encounter. You have documents in Hebrew, Arabic, Judeo-Arabic, which is actually a fusion of Hebrew with Arabic and Hebrew letters. You have scholarly literature now from 100 years or so now in English, German, French, and a bunch of other languages. So it really is kind of a great test bed to test how well some of these models are in their multilingual sense. And explore kind of questions like few-shot and transfer learning. For instance, if you had a model, an LLM that worked well in Hebrew and Arabic, could it understand Judeo-Arabic with only a few examples? And really, we can use it to look at questions of how multilingual are LLMs really, and how well do they do on very limited, low-resource languages. Another sense, and particularly relevant for this tutorial, is fundamentally interesting from a multimodality perspective because many of these documents lack transcriptions. They're, as we just saw, fragmented across many different collections. So basically, based on what I said earlier, should automatically be thinking, okay, we now need multimodal representations where one fragment has a high cosine similarity with its other potential fragments or joins across collections. And fundamentally, we, using any type of AI, and it really needs to reason about very wide range structures of different types of documents, from marriage contracts to pages of religious text. Finally, it gets really into this idea of like what is a useful representation, which goes long, which is a fundamental question in AI and representation learning in general. These documents have many different attributes. They have like things like script and handwriting, period written, the actual content of the document, the fundamental type of the document. So AI implementation is kind of like, oh, if we create like a high dimensional vector embedding of one of these documents, what should that really represent? And if we apply these multimodal embeddings, what do they weigh heavily? Do they weigh the visual features? Do they weigh the textual content? What is kind of, we have a fused representation of both the text and the image, like what's really going into that representation, and how can that, and furthermore, can we disentangle that representation and do specific dimensions of, say, like it's a 128 dimensional vector, do specific dimensions that correlate to these different attributes of the document. So with that said, one of the big open source projects I've been working on recently is this idea of the Cairo Geniza AI project, and the idea is to provide a kind of a modern search interface to search specific fragments across all the different collections, create basically a RAG assistant that unites the primary source fragments with the secondary scholarly literature, and then have interactive visualizations of the embedding space that people can kind of browse, and long-term try to train OCR and kind of multimodal LLMs for transcription and visual question and answering on these documents. And specifically for this tutorial, there are kind of three things I want to highlight. One is probing the embedding space. Two is the limit of multimodal LLMs for right to left languages. and free is how to process semi-structured information in kind of a hybrid manner. I specifically chose these free because I think even though this project in some ways is highly focused, these free are the most generalizable to any type of multimodal AI application. And so like what we'll see with probing the embedding space is fundamentally with RAG, usually the limitation is usually the retrieval portion. Like if you retrieve the right documents in a RAG system, usually the LLM, obviously not all cases, but usually it will answer the question correctly. But when retrieval fails, that's often when you get hallucinations, other weird behavior. And how are most searches done nowadays? Well, they're done semantically. They're done using embeddings. So probing the embedding space of whatever type of project you're working on, I think is really important, even if it's single modality, but particularly for multimodality, and kind of understanding the geometry of that is very important. And then secondly, this idea of the limits of generic multimodal LLMs. So these vision LLMs are very good, and they can work very well when they quote unquote work, but there are of course times they don't work, and as we'll see, they generate some really weird hallucinations, as we'll see in a second. And this isn't just limited to the Cairo-Geniza. It is harder on, of course, Hebrew and Arabic text because these models don't have as much training data, but this can also happen just on other types of text, even with Latin characters. I've seen it happen in some of our financial applications, unfortunately. So it's important to know about that and basically be able to mitigate that. It's of course a lot rarer on Latin characters, but it does happen. And finally, there's this kind of idea of how do we, knowing this happens, how do we process both the fragments and then secondary sources, maintaining the structure and creating good question and answering capabilities. So then we'll talk about that in a second. So with that kind of said, I'm going to begin to jump into visualizing the embedding space. As you know, there are three main visualization methods. You can use PCA, T-sign, and UMAP. We don't have time to go into all the details about the subtleties between each. PCA is usually a very quick method. T-sign takes a little bit more time but produces better clusters, particularly at the local level. And UMAP is like generally producing clusters that work very well at kind of the global level. So now I'm going to go a bit into probing the embedding space. And by the way, all this code is open source, so I'm just pulling up the notebook here. So one of the first things I did actually with the Cairo-Geniza was I created this kind of notebook on using Clip to create embeddings and just seeing how well it worked with different concepts in general. And so yeah, you can play around with this notebook later. I checked it just a few days ago and it still ran. But one of the first things I saw was, I kind of looked at was this idea of just plotting different concepts. And like here I plotted different kind of Jewish textual documents and saw if they formed their own unique clusters. And then I applied some just other things like colors and saw how they were kind of Clip did at creating these embeddings and just the geometry of this space. Very simple plot, kind of gets and starts to show the basics of some of the embedding space. Then, you can generate these two, the second part in the same notebook too. However, I did create just a static image from it. I'll show here. Then what I did is then I actually went and did create image embedding. So basically, I started to then actually take images of these different things and then plot how they kind of clustered in the embedding space. So there you can see there's kind of like a cluster of animals, which makes sense. Here's a cluster of the different types of Jewish text. And then here's like, clusters of other types of documents and colors. And so this was useful, and I could see, okay, Clip, it might not be perfect, but it does seem to somewhat understand these are Jewish texts and should be like distinct from these other types of things in the embedding space. Kind of the continuation of that was then when I created the entire site, and this site is actually live, and anyone can go to it. To create the AI site, I created this collection explorer. So, by the way, this is kind of the user interface. This is the RAG assistant. Here's where people can search. But for our purposes, we're going to look at this explorer. So I'm going to click the full index explorer. And this will take a while since it's going to, so far of the basically 200 or 1,000 or so unique shelf marks in the Chirogonisa, I've indexed about 40,000 in Elasticsearch. And then this will load these 40,000 into interactive visualization in just a second. So it does take some time, but what we'll see when it kind of finishes loading, which hopefully won't be a while, is that we will see there are some clusters that start to form in terms of language, but also particularly collections in the Chirogonisa, such as, and how the documents were then grouped by library. So we'll see all that in terms of different collections. Sometimes this takes a while. By the way, I'm running this whole kind of app on a Mac Studio too, so it's not a production grade server. I'm running out of my apartment, but the idea is that it will load. And actually, why it's loading, that might be a good idea to show some of the code here. So this code, as I said, is all open source. I created this repository called Historical Document Analysis. I guess kind of stupidly didn't put it actually in the PyData link here, but it is open and accessible. Anyone can browse it and see this code and maybe even use some of these ideas on your own projects. So here we see the kind of embedding space of the Chirogonisa. And right here it's color-coded by language, so we do see a lot of documents, for instance, in Judeo-Arabic, a lot in kind of Hebrew as well. And then language, you can see that really some unique clusters are obviously forming in terms of language. You can see that, I think, but it's probably not as, for instance, important as other characteristics. By the way, so when you click on one, it pops up the document in the UI, so then you can actually look at it. So this is really useful for analyzing the clusters. I actually think a visualization tool like this could be useful for a lot of RAG applications. Not just this one, but a lot of multimodal ones. But this cluster itself is text only, so it's really using only the text, particularly the catalog data. So that's why we're seeing some of that behavior. Now, if I go here and I go to collection, we will see that like a lot of the documents, since they're using the library catalog data, we do see very distinct clusters here because the way libraries catalog these documents, they have their own kind of metadata structure. So you do see like particularly Cambridge documents forming clusters, and then even sub-series of clusters. Like I think this is this subcluster here is like of the Manchester P series, for instance. And actually, I mean, this is useful because we can see long-term we probably actually don't want this because these collections are somewhat arbitrary of just who loaded Geniza documents up onto their card and brought them back to the library, wherever. But it does show that the embeddings have at least sub-meaning, and by visualizing the embedding space, then this is kind of the crucial idea from this is long-term we can then fine-tune models and begin to explore different ways of creating the embeddings to show so that the geometry will be in a way we want. And I think that's really important for any type of RAG application, including multimodal ones, particularly multimodal ones.
Question?
Yeah.
Actually, contrarian question. So for us scientists, we love visualization to better understand things.
Yeah.
But you said this visualization can help you train better models. How does visualizing actually helps you improve the model?
So yeah, one of the ways I think that can help is, I mean, we see right now it's primarily the thing that's weighting heavily is kind of the different collection and cluster metadata. So in future models, we wanted to maybe actually even before we train models to standardize the data by collection so that the metadata had all the same formats so we wouldn't see such distinct clusters for different collections, and then long-term, if we wanted to, say, like fine-tune nomics, we would actually then put in the training data. So, like for those example text and image pairs, we would then have them create those pairs so that it would create those embeddings weighing either the image component higher or the catalog metadata in that unified representation. So that's kind of, I guess, the answer. So I'm going to go back to my slides now. So we just talked about this. Another fundamental thing is we have all these powerful LLMs, and we sometimes just assume they can work on certain types of text. And as I've quickly discovered, and I'll show you, they don't always work well on particularly non-Latin text. But as I said, these lessons are kind of related because if it's usually a limit of the vision encoder. I'm going to talk about it in a second why that's important. So, before even trying to get these models to transcribe, say, the Cairo-Geniza text, because those are a lot of very hard handwritings, I just gave it basically a more standard block Hebrew text and asked it to essentially transcribe parts of it. And I asked it specifically to transcribe this column, which is basically if you're familiar with the Talmud, is the commentary of Rashi. And I basically asked it to do it. This was Gemini. I was playing with Gemini because I assumed Gemini would work probably better than Gemma. So I was just playing out with the UI. And this was kind of the results table. It just completely hallucinated a lot of plausible sounding text. I don't expect most people to tell the difference, but it started talking about things that weren't in the text at all. But it sounded plausible because it did cite like kind of Talmudic or names and stuff. And because what happened was, I think, is the vision encoder never got this type of style of Hebrew. So then instead of actually generating kind of real text based on the Hebrew characters, it just started to generate what it thought a Talmud commentary should sound like. And then even worse, over time it doubled down on its hallucination, said it was the ground truth. In some places only did 2 words when there were clearly like 20 Hebrew words. So, yeah.
Do you think it has to do with more with the character set or the source language? I mean, if it was modern Hebrew, would it do that much better? Or?
Yeah. So I mean, what I discovered is that this particular model wasn't doing very well on any type of Hebrew or kind of Semitic alphabet. It has gotten slightly better with, Gemini Free was released more recently, and that is better at just standard Hebrew at least. I do think it's slowly getting better, but particularly specialized subsets like cursive Hebrew, Rashi script, it's still failing pretty badly on. So that's kind of what I learned with this, but then kind of like one of the fundamental things then I learned okay, so it didn't work. We go now to fine tune a model to actually be able to look better at Hebrew. A lot of people use LoRa, and doing LoRa here is not actually going to work, at least not the way standard LoRa is done. Because remember, standard LoRa, you're usually freezing the layers. You're freezing like the vision encoder layer, you're freezing the projector, and particularly here the main issue was that it wasn't understanding the fundamental Hebrew characters or the type of script. So when you freeze like the vision layers, what happens in LoRa is it just learns to generate more plausible sounding text that is nonetheless not grounded in the image in any way. Hopefully that will come back on in a second. So what I saw specifically in training was then, I'm going to pull this back up. What I saw specifically in training then quite a bit was there would be initial decrease in loss with this, but then the loss would basically plateau and not really go down any further and would be quite noisy because essentially, as I said, what was happening is it was learning to generate more text that more fit the distribution of, say, the Talmud, but not text that was actually based on the image of the Talmud given. And so that's obviously a problem, and to rectify that, if you do a WARA, or if you do want to fine tune one of these VLMs or any type of LM really, is to, you need to fine tune the actual image encoder portion of it. You can't just stick a WARA onto the end and expect it to work. So then basically after this, I kind of went back and I started to look more towards, okay, in some cases, particularly in these cases with novel languages, using a more traditional OCR approach might be better than using a multimodal LLM. And there are some definite advantages, I think, to using OCR. One is OCR models might get the characters wrong. They might not pick up the characters, but it's not going to completely hallucinate them. Usually if an OCR model doesn't detect a character, it might, it will just show nothing there. It's not going to generate something that sounds plausible. This is specifically something that happens a lot with VLMs, because with the VLM, since you have the vision encoder, if the vision encoder doesn't pick something up, then the text portion just generates plausible sounding text based on the prompt. So, so then basically I started looking in specifically for processing kind of secondary sources. I started having the idea of, okay, maybe like the primary texts are too hard to parse at this point using VLMs, or even OCR do not work currently well on the actual fragments, because we saw those are very hard. But basically the secondary sources, which those two combine a lot of Hebrew and also tables with English and other things like that. We could do like a general OCR step using a traditional OCR model. And then we could apply an LLM as a secondary step to that. So just for example, some of these pages on literature on the Cairo-Geniza, you have like these tables. This is somewhat analogous to some of the tables we have in finance. You also have these, text and footnotes. Another big thing too is you have transcriptions and references to class marks, and you want to extract the transcription separately, because ideally then that could form parallel training data for actually then fine-tuning a model to be able to transcribe given the image. So you have these kind of like structured pages, and you just apply OCR, it loses the structure and doesn't maintain the stuff with the transcriptions. So basically the idea then was to have a multi-step process, and before going in, and you might be wondering why not use the LLM from the beginning, but as I kind of outlined, LLMs seem to be particularly poor, the vision layers, at doing Hebrew, even in some cases modern Hebrew compared to OCR. And it can also, I think just generic OCR can actually act as a verification check on the LLM outputs versus, so then you could compare the two. And then also something I've seen even in some of our financial applications with VLMs is the non-deterministic nature of LLMs. So like OCR model, if you use the same seed and everything, it will always give the same output. Particularly a VLM, you now have two different components, the vision component and the text component, and the outputs can vary. So some questions on those, even in finance, I've asked the same question several times, and it gives a different answer for what the text in a table is, for instance. So, so it's kind of an example, and going back more to the code side now. I created this basically multi-step pipeline. Actually, for this part, I'm going to quickly switch to mirroring, because right now I don't have this on my main display. Mirror. So basically here, if here's like a example of the complete pipeline for processing these kind of secondary sources. Basically, we start by first of all loading the metadata. So like an article isn't just the page we're looking at, but there's an author, a title, and everything. So basically, first we have to load kind of all that. I'm just going to increase that size. Load the metadata. Then I create what's called a structured JSON LLM, and I'll show this right now. But the idea of this is fundamentally it takes the OCR text and image from the LLM, and then it extracts it to kind of standardized JSON data. And instead of trying to recognize the characters itself, as you can see from the kind of prompt I've created, I basically explicitly say do not ever attempt to transcribe the document, basically only use the OCR and the image to arrange the given text. And I saw this greatly helped because then with these pages, because then instead of trying to transcribe, say those transcriptions or text, raw text, all I had to do was basically arrange the OCR results from the document using the image into this structured JSON format. And so that was very useful. And there are better ways to do this. Actually, I learned something in just the last tutorial on how to maybe use PyData to validate this. But the idea is then but the core idea here is to only use the LM to arrange this thing according to the original image, not try to actually transcribe it itself. Oh yeah.
So are you just getting the bounding box for, let's say you have a passage of Hebrew, you're just getting the bounding box and then you're maybe doing some other cleanup and then passing it to the OCR layer, in essence?
Yeah, so right now what I'm doing is, I'm doing the OCR and I am getting the coordinates and I'm getting the raw text from OCR. And then I'm passing that to the LLM to basically then use that plus the image, the actual image, to reconstruct the page into a JSON parsed format is essentially what I'm doing. So it's leveraging both the OCR model and the VLM, but it's not asking the VLM to try to transcribe anything because then that's where you sometimes get weird hallucinations. So that's kind of going through that's kind of the core of the Cairo-Geniza example. There's a lot more things I could go into, but that's kind of, I think, wraps up 3 important ideas from text and images, and specifically those. Before I actually move on, I was going to do questions at the end, but this is kind of a natural stopping point. Does anyone have questions about text and image, multimodal, in that sense or anything? Yeah.
So I'm not usually aware of how they train visual encoders, right? So usually do they give let's say do they give a character and then they give the piece of text, which is like the translated version to the visual encoder during training, or is it usually passages of text? How do they train it usually?
So the answer is for the vision encoders and the VLM, that's what you're asking about?
Yes.
Okay, so the answer is it varies. In general, those are trained holistically, so you supply the full image of the document and the text, and then you provide the corresponding document. So it does not, so that's an important distinction from OCR. It does not learn character by character. It learns basically the training example, one full training example at a time, and that's why sometimes you do see it misrepresenting characters. There was particularly a paper a while ago called Donut, where they basically did that exact thing, where they don't have the necessarily aligned things from each output. They just have the image and then the full text output and then feed it together. Actually, that raises an important. I had an actual training notebook too, where I fine-tuned Gemma. I forgot where I put it, but I had, and there you can see basically when I was fine-tuning Gemma. So let me see if I can find this right now. Oh yeah, this is still mirrored, which is good. Yeah, I was going to show this, but then I decided this might be a bit more detail. But basically, when I was fine-tuning Gemma, I was loading specific sections of the Rashi, Tosafot as different parts of the image, and then having the image cropped. And then basically what happened was then these different sections were then given to that LLM each at a time. So it was not character by character. It was learning to transcribe a specific section at a time. So any more questions on the text and image is? Okay, in that case, I guess I'll move on to the next part, which is kind of more of the frontier, or how we can explore this idea of aligning modalities more globally than just text and images. And so one of the first papers that I kind of found interesting in this idea, and which aligns with some of my other research interests rather, is this idea of times clip. And basically with times clip, it's very, very similar to like the kind of clip you saw for the text and image. This was a recent paper at NLP this year. But the idea was you would have, say, like a time series embedding, and then you would have a time series embedding, and then also text that corresponded with it, and then you would, in the same fashion, train the model using the time series encoder and the text encoder. And then the idea with that is then you're visually grounding the time series to the text. So the main idea is that then you could say, like, for instance, if you had had a time series of different, like, say, machines operating, and you had one where it failed, you know, the time series where it failed, you could then have literally a similar type of retrieval where, you know, failing machine, the text of that would have a high cosine similarity with the actual time series embedding for a failing machine. Or something that I've been looking at for my research is particularly related to flash floods, is then like you could then search over a database of like river flows and rainfall time series embeddings, like for something near flash flood, or like, you know, future flash flood or critical warning level or different things. But basically the idea is you semantically ground the text to the time series embedding rather than just having it be entirely separate. So moving on from that, there have been, and kind of related to some of those thoughts, there have been several interesting papers that have taken this idea somewhat further for climate models, where you might have a bunch of different input, which is like time series weather data in this case, and then you also have images, actual images, and then you feed those into a large language model as different features, and then you have that predict various spatial temporal kind of predictions based on that data. I think this is definitely interesting and useful. Because one of the big things too, after having worked a long time in time series forecasting and time series analysis with deep learning models, is that often these deep learning models do not learn the basic underlying physics of the time series. So even like when you had, say, like a flash flood model, even if you trained it on a bunch of data, it would learn maybe to predict some of the distribution of the river flow, but it wouldn't necessarily implicitly understand the multivariate relationship between even something simple like rainfall and a bunch of river flow. It would just learn to predict an overall distribution. And so one of the ideas with this too is that you could basically then, like have a time series embedding, and then you could have the LLM and have actually pass, you know, explicit physics knowledge in the form of text to the LLM, and it could fuse the two to, in this way, form better predictions based on both the physics knowledge and the time series embedding. So that's kind of one of those ideas there. Oh yeah.
Have you tried this with asset prices?
I have not, no.
That's exactly what you would do, right? You would look at news every day, and then you would try to match that with how the prices have been changing over time. I mean, news is just one.
Yeah, that's a good point. Yeah, I haven't done with asset prices explicitly, but I have seen papers that have talked about like, you know, stock prediction informed on news articles, and they've created text embeddings based on the news and fuse those with the time series. Yeah.
But for time series forecasting, I think there are a couple of approaches where they just give the numerical data, right? Like
Yeah.
for example, let's say we have like preventive maintenance for machines, right? So we get the acceleration data, for example.
Yeah.
And then they give like the 6 month or 8 month data over time, and then they put a LoRa adapter at the end for it. And like it seems to give good enough results. So how would this approach, like how is it better? Like maybe compared to the traditional LoRa-based approach.
So you're saying compared to just traditional, just numeric-based approaches?
Just numeric, you give it to the LLM, and then you have a LoRa adapter at the end, which kind of predicts if there's going to be a machine failure or not for the specific example.
Oh, okay, so you're saying you're passing the numerical data to an LLM and
Like
then...
acceleration data of a machine. Like your fridge is there, so you have like your temperature data
yeah.
and your
Yeah.
vibration data.
Yeah, so yeah, that's a good point. There have been some things. One of the advantages of different approaches like this, actually creating a time series embedding though, is when you pass it, and you've probably seen this before, that LLMs in general don't do well at math or in general at tons of different numbers at once. So actually creating a time series embedding and then fusing that with cross attention with the other types of modalities, in essence generates a more holistic representation, then that's easier to reason on. And then if you just say pass a bunch of numbers as text, is I think what you were getting at, right? So that's kind of the short answer of that part. So then specifically, and a lot of stuff I've been working on with river flow forecasting, I know this didn't, this table didn't translate well, but a lot of these rivers now have webcams as well, which is somewhat useful because based on those, we can learn then what the river kind of looks like with similar time series or different river levels on the gauge. And so basically in theory, we create a model like, for instance, here we could then create a time series embedding, an image embedding of what the actual flow of the river is visually. Then it's easier to then estimate, like create, hopefully then long-term create a model that can translate modality to modality. So then if we do think, okay, we're getting like say a flash flood in this area, we can then more know exactly where it would overflow, what path it might take. So this idea of using both time series, visually grounded time series for different parts of the river is very useful potentially with the actual image embedding. The other thing was then also using satellite imagery too, because satellite imagery is, you could have, say, then the webcam as one kind of modality of image, but then also satellite imagery as another type of image, and feed both these types of images along with a time series embedding, and then reason on both of those to be able to kind of do kind of more in-depth multimodal reasoning on that. So does anyone have any questions on that? Okay. So what I was going to do then was I was going to also actually, before I jump into some of the code examples of multimodal time series, is there any other parts of the kind of presentation people were wondering about or kind of want more details on? I'm for once actually running ahead of schedule on time right now, so from all my rehearsals. Yeah.
Your like personal repo with the code for some of these examples, is that available somewhere so we can look at it afterwards, or?
Yeah, so
If it's not public, that's cool too.
No. So yeah, I'll clarify a bit about some of the code. So basically, for the Cairo Geniza, the whole Cairo Geniza web app, this search, everything like that, this is divided over kind of two repositories. Both are open sourced. One is this repository, historical document analysis, and yeah, this might be actually a good segue to talk more about some of the architecture here, but this is primarily this repo does the indexing for all of it. So this will, with this repo, you can ingest the Cairo Geniza data and then basically index it into the Elasticsearch index that then is searchable by the second repo, which does the actual back end and front end, and that is this repo called Geniza Search. And so this Geniza Search repo is what does the actual visualization. You can see it's a mix of JavaScript and Python, and this, oh, well, you can't, the screen just went out, but then basically, fundamentally, this can be run, and I was actually for a while thinking of doing this in the tutorial, but it actually requires a fair amount of memory. But this can all be composed via Docker Compose. So basically the entire front end, back end, and embedding service can run via Docker Compose, where we have essentially, well actually here we have 5 different containers. We have Elasticsearch as a container, Kibana as a container, because then I look at that for the documents. Then we have the front end, and then we have the back end, which is Python, and then we have the embedding service. And I actually separated the embedding service from the generic back end because the Nomics embedding model is actually the largest thing in this whole configuration. And it was really, it's often the bottleneck. So if we're actually talking about latency on the site, like when someone searches stuff, it's often usually the embedding model that gets overloaded, like on a search. So by Dockerizing that into a separate service, for instance, it was a lot easier to parallelize the searches, about as you'd expect. So that's kind of how that works. And then for the chat assistant, I didn't talk much about that, but that actually is running on Olama. Unfortunately, there's an Olama talk going on currently to this one, so it would have been fun to go to that too. But that uses Olama on the back end, and basically you just have to set up an Olama endpoint, and then you can do a similar type of kind of analysis through there. So yeah, that's kind of how the repos are laid out. The fine-tuning code is, so if people wanted to see the fine-tuning code, that is all in that kind of first repo, the multimodal document analysis repo. And the idea with that historical document analysis repo is for a long time to factor this into a Python package where people can easily use this on any type of historical documents, not just generally the Cairo Geniza. So that's kind of there. And then within here, you see different folders, fine-tuning. So I did some fine-tuning of clip on Hebrew, donut on Hebrew, like I mentioned before. Here, the fine-tuning of Gemma you saw in the notebook primarily uses this example, which hopefully the screen will come back on in a second. But that's kind of how the whole thing kind of links together and can be used holistically. So yeah, I decided not to do too deep of a dive into any of the code, but then similarly the LLMs, the structured JSON LLM is here. This can basically, as I said, parse everything into a structured, the structured thing that I showed before with the secondary sources. And yeah, as I said, long term, the idea is to have this as actually a PY package that people, and then it will require some cleanup, but then that people could use on any type of historical documents, and maybe it could even work on some other documents. I don't know, but right now that's kind of what I'm targeting. So yeah, that's kind of the URL. I'll try to post. Are people in the PyData Boston Slack group? I don't. Well, I think you can join it, and I'll try to post most there, or I might see if there's other way to do that. But yeah, these are all publicly accessible. So, any other questions on that? Yeah.
I have completely different question on different application of multimodal learning and reasoning. Maybe you can give me pointers.
Yeah.
So I'm interested in a application to help me learn when I'm listening to a lecture, something that would record the sound and as well as snapshot of the presentation and process everything to help me digest and learn the material that's being presented. So it's sort of multimodal learning, right? So do you have any pointers, maybe successful applications or some research in this area?
Yeah, so yeah, I think you're talking about text, audio, and image models that combine all three, or even a video LLM. Yeah, so I have seen there has been some research on, I forget where I had it. There was like, there was actually a video LLM. I saw it somewhere. I forgot what it was called. That like did reason over kind of audio, text, and I'm gonna see if I can find it. No, that's generation. Oh yeah, audio visual LM for video understanding. Yeah, this is what I saw before. So yeah, there are papers coming out that basically combine both audio and visual for specific understanding. So like this one I think would be useful for that case. I think actually some of the big provider LLMs, I know GPT-5, I think has audio, right? I can reason over audio. I don't know why this is taking so long to load. Oh yeah, this was the one I saw. So this one actually is kind of interesting. It takes audio, video, and then even text all together, and basically fuses them. It creates basically a video embedding, an audio embedding, and then a text embedding. So something like that I think would probably be the most relevant. I don't know if this has been available for any kind of production API or something like this, but I think this is this audio visual question and answering I think is somewhat related to what you're looking at, and yeah, I could maybe help with that as well. So any other questions? Anyone want me to return to any different topics? As I said, actually, normally on my timings when I timed this out, it was longer, but here I'm seem to be running ahead of time.
Are you going to present flow forecast package?
What?
Flow forecast, it's your package, right? That's what you used for flood.
Yeah. So that's one of the using the that's using neural networks on time series forecasting, and it's also just general time series forecasting using deep learning. And I have so yeah, this was the primary repo I used for quite a while for that. I have actually started to try to implement multimodal things that allow the fusion of the images. I haven't fully done it, but yeah, that's kind of what that yeah.
So for search and TSN, were you using clip embeddings, clip model to generate embeddings for the image and text?
So right now for the actual Cairo Geniza AI search, I'm using the Nomics text embeddings primarily. I'm doing that primarily, and they're actually working fairly well. So like if you search, like for instance, ketubah in Hebrew, which is basically a marriage contract, it does return marriage contracts and things like that. And then I haven't really fully dived into actually using the image embeddings because, as I said, both Nomics and Clip were trained on very general documents. So I think for the images to actually be useful when I've created full image embeddings, we really need to train the models. Like this is a partially torn image on of a ketubah or partially torn faded page. So I've been actually slowly putting training data into the right format to make the image embeddings work better. Because that is one thing I've seen that, like particularly for such a specific problem as this, a lot of these models are not going to be able to really reason about some of these images out of the box at all. So that's why they really need to be fine-tuned. But yeah, I think that actually gets to another interesting point that I'll just throw in there since we have some extra time is if anyone needs to train Nomics, there's actually the full training data set that Nomics used when they when they did the model here on Hugging Face. And so if you look at the actual kinds of queries, strings, and images here, for instance, you can see that a lot of these are about specifically ArcSiv papers and, about specific diagrams, like comparing diagrams, and then it would have, say, like an image of that page. So basically, in order to train Nomics, you have to format your data into a similar training format, which is something I've been working on. So like instead of having like questions about diagrams here, and for like the Cairo Geniza, what I'm going to have is I'm going to have like images of those different fragments, and then be like, what does this, what type of document is this fragment or whatever, and then is a fragment of, for instance, a marriage contract, or like basically different queries that can align those text and image embeddings. So that is something that yeah, you can definitely fine tune nomics, and I think that's an interesting thing to do. I haven't really done it yet, but that's why I'm kind of working on, and you can see exactly how nomics is trained and like if it will work well based on some of this. So, and then again, beneath the hood is of nomics. I didn't mention this as before. It's actually the Cole-Quinn model. So remember, nomics is kind of a VLM. So this Vision LLM, you can actually sometimes substitute for other VLMs, but right now they use the Cole-Quinn 2.5 as a backbone. So I would be kind of interested if other newer models you could substitute in as a backbone, and if those would provide kind of interesting things. So yeah, any other questions? Oh yeah.
But for now, the easiest way, let's say I have like multimodal data, in the sense I have documents and images. So for now, the easiest way would be to kind of transfer my image into text and then embed it with like a traditional text embedding model, right? That seems to be the easiest way.
Well, it's the easiest way right now on the Cairo Geniza. Actually, these image embeddings work really well on more languages. For instance, at work, we recently switched to image embeddings of all of our tables, so we don't actually transcribe them the data at all. And for their cohere embeddings work very well at just retrieving the image embeddings. And I'd say actually for a lot of applications in the business world, they work pretty well because that's again what these models like nomics, multimodal are trained on. The only reason it doesn't really work on the Cairo Geniza now is these are obviously non-line scripts and they're very specific types of documents. They're tattered, they're torn, they're not like a modern PDF at all. So that's kind of why it's not picking up relevant visual features from them. But I actually think for most modern types of documents, the image embeddings or a hybrid image and text embeddings now work very well. So. So any other questions, final thoughts? Okay, and then I'll wrap up there and give you guys your time back. Again, also like one last thing, I think I had a slide of URLs here too. So yeah, since I know people might not see this might be useful to see. These are the different URLs, basically polyagent, the hydrology project, all the different things. I've written about this kind of extensively in more detail on my blog too, and I'm going to have some more blog posts coming out on multimodal learning. And again, if you're interested in volunteering on some open source work, polyagent, we're doing a lot of cool projects, not just the Cairo Geniza, but several, there's actually fine-tuning of VLM on Ukrainian now too, and some of those other languages that haven't been really studied well. So again, thanks everyone for coming out. I hope you learned something. So.